As I was mentioned before, I'm going to talk to you about a bit of neutrinos and how the quest to understand these particles led us to breakthrough discoveries. And I think since we have measured neutrino masses and basically are a proof of the existence of beyond the standard model, in the future we will also lead us to other breakthrough discoveries. So I wanted to do a bit different approach here. I wanted to do since the title says epic poem, I wanted to use the structure of an epic poem like the Iliad or Odyssey. And they usually start like in the middle of things. So let's say in the middle of the war, in the middle of the budget. So for our case, what we wanted to do is first establish what is the status of neutrino physics today. And because of, I'm going to introduce a lot of, jargon, which is probably not familiar with some people. I will go back to the past and understand briefly how did we get here, how we know that neutrino physics are this new portal to understand beyond the standard model physics. After that, I'm going to talk about what lies in the future and some directions that I find particularly interesting to solve open questions in neutrino physics. So as I was saying, we are going to start in the middle of things, in medias res, and I forgot to mention something important. I will take as a blueprint the Aeneid, which is basically the journey from Aeneas, from Troy, to go to Latium, to go to basically Italy. And this epic starts in the middle of a storm, which is basically the goddess Juno is mad at Aeneas and basically departs him and throws him to Carthage. I will start with the standard model, but I'm not saying anything that the standard model is in the middle of a storm. It's just, let's say, it started like this. So let me just remind you briefly about the standard model. Basically, our standard model describes the electromagnetic, weak, and strange.
So you don't need to.
OK. So yeah, I just wanted to mention that from all these particles, I will focus, and our heroes will be the neutrinos, the three neutrinos that, by construction, are massless in the standard model. So this is done by construction. But of course, we know that neutrinos have masses and present mixing. And I will come back a bit later on understand how this happened. How do we know that neutrinos are massive? But what I want to emphasize here is that this constitutes an existence of a proof of the existence of beyond the standard model physics. But wait, we can think, and maybe it's just adding new particles, doing the same Higgs mechanism that we did for the other charged leptons. But neutrinos are weird, in the sense that when we look, for instance, what are the masses of all charged leptons, all charged fermions, so the quarks here, the charged lepton here, and we compare what we can extract about the neutrino masses. For instance, we know that they cannot be massive than the electron volt scale. And from some experiments, I will come back to this later, we know that the masses, for instance, one state cannot be lighter than 10⁻²⁻² electron volt. So as you can see here, there is a huge gap between the mass of the electron and the electron volt scale. It's about 6 orders of magnitude. So one may wonder, why do we have this gap? What is this gap telling us something about the origin of neutrino masses? It's telling us that maybe the neutrino masses are coming from a totally different physics than the mass of these other particles, other different scales. There are, however, other fundamental questions. One that I will particularly focus on is, what is the fundamental neutrino nature? By this, I mean if neutrinos are Dirac or Majorana. And this only happens for neutrinos, because the other particles, since they are charged, you won't have this kind of problems. Other is, since we have this weird situation, do neutrinos talk with a hidden sector of particles that only talk with the standard model via neutrinos? And finally, we may wonder, well, when we look about mixing in the lepton sector, and we compare it with the quark sector, we find that they have totally different shapes. Is it something telling us about the origin of neutrino masses? OK, but how did we get here? So as I was saying, I have just introduced a lot of jargon about mixing, masses, the standard model. But someone may be asking, well, what is even a neutrino? So let me just remind you briefly and take a journey from basically similar to what Aeneas did from the fall of Troy to, at some point, it will stop, of course. But the Aeneid begins, let's say the journey of Aeneas begins with him leaving the fall after Troy fell. In our case, neutrinos basically appear because when we look at the spectrum of the energy of the electrons that are produced in beta decays, it's continuous. And this was basically telling us that there was some ease in energy that we were not seeing, because if there was no missing energy, we would see only electrons with some specific energy. But some people suggested maybe we should do like with Trojan, burn everything, assume that there is no conservation of energy at the subatomic level. But Pauli proposed the neutrino hypothesis, in which basically you have a neutron, and this decays producing not only electrons, but also a neutrino, an additional particle that is not seen, and is basically the responsible of taking the rest of the energy that we observe from beta decays. Of course, now we can keep with our journey. Next step, of course, neutrinos were detected by Cowans and Reines in the 50s. But I want to do a stop in the island of Delos, and my analogy will be that something which is crucial about weak interactions is the existence of parity violation. Parity violation is telling us that neutrinos that are produced in beta decays are basically left-handed particles, or the antineutrinos are right-handed particles. And Li and Yang noticed that this can happen if there are only left-handed neutrinos and right-handed antineutrinos. This would suggest that neutrinos are actually massless particles. Moreover, at this point, there was no evidence of the existence of neutrino masses. So basically, people started to assume this is the most economical way to talk about neutrinos. They are basically massless particles. So let's basically assume that they are massless particles. After that, basically, in the Aeneas reached and basically found a city, thinking that this is the promised land. In our case, our promised land is the standard model, which is basically established with the existence of 3 neutrinos, each one related to a generation. And we thought it was the promised land because neutrinos are basically massless. We know about the interaction, so we just need to use them for other things. However, as what happened with Aeneas in Pergamum, many things started to happen to telling us that we were not in the promised land. And basically what happens is that we started to observe several anomalies with neutrino experiments. So let me be a bit more in detail here, and I will just choose one specific case which will be important later, which is the case of looking for atmospheric neutrinos. So atmospheric neutrinos are basically produced when you have incoming cosmic rays. These cosmic rays interact with the atmosphere, producing a cascade of mesons, which basically decay, producing neutrinos. Interestingly, you are able to predict what is the flux of neutrinos at any given position of the Earth, let's say modulo some uncertainties. But in principle, if you put some detector at some point, you would be able to see how is the flux of neutrinos arriving at your detector. And this will have some specific dependence on your zenith angle with the zenith angle, right? So the experiment Super Kamiokande, basically, or actually started with Kamiokande, they started to observe an anomaly with the number of events that are produced when you look at these atmospheric neutrinos. So how does Super Kamiokande work? Super Kamiokande basically is a water Cherenkov tank. Basically, when a neutrino interacts and produces a muon or an electron, this particle propagates faster than light in water, and it produces basically Cherenkov radiation. Depending on the initial neutrino, if it's a nu mu or nu e, what happens is that it will give a different signal from one of the other. The reason is that when a muon neutrino interacts and produces a muon, this muon only radiates and produces this cone, and it produces a very neat cone, as you can see here. However, if the interaction produces an electron, this basically produces an electron shower, and you see many electrons, and each one will produce a Cherenkov ring, and basically will overlap, producing this fuzzy ring here. So there is a way to differentiate between nu mu's and nu e's that are in this type of experiment. The thing is that when we start to look at the dependence of the number of events with respect to the distance they travel, by this I mean the cosine of the zenith angle, we observe that there is a deficit of neutrinos when we look at the neutrinos that are coming from below. If you compare here, basically -1 means this is like the zenith angle, basically. if this is -1, neutrinos are coming from below. And you see that there is a very different number of events to what's expected here. So what is expected here is basically this red dashed line, and basically coming from some specific simulations of the atmospheric neutrino flux. So you see that there is a specific dependence with the distance that these neutrinos have been traveled. On the other hand, we see that there is no much effect of electrons, although you can see that there is a bit of a difference between this green line and the red dashed line that I will come back later, what this green line means. So the conclusion is that Super K is observing a neutrino change that not only depends on the distance, as we can see here in this type of plots. So how do we explain the existence of this change in the change of neutrinos depending on the distance? So basically, we can assume that neutrinos are massive particles, and they present mixing, similar to what happened with quarks. In this case, what we say is that the neutrinos that we are calling flavor against states, which are produced in beta decays or in other weak interactions, are not, are a linear composition of the eigenvalues of the free Hamiltonian. And the, let's say, proportionality matrix will be this PMNS matrix that I was talking in the beginning that relates to the lepton mixing. So because of this mixing, there will be a non-zero transition probability, and this transition probability will depend on the distance and the energy of the neutrinos. But of course, if we want to compute this probability, 3 by 3 is a bit complicated, so maybe we can just simplify things a bit and consider two flavors. And in this case, we will consider basically this mixing, and we will parameterize in terms of this mixing angle here. So when we compute the probability, we observe that, for instance, the probability of a new mu, a mu neutrino, keeping its flavor, has this oscillatory shape. So it's telling us this depends on the distance. And interestingly, also depends on the energy. So here, sorry, there was an animation here. I just wanted to do the analog thing to explain neutrino oscillations with this coupled pendula. And basically, if you start with a new mu state, after some time, or for the case of neutrino oscillation, some distance, you would have a non-zero probability, probably a probability close to be maximal to detect an electron neutrino. So our task would be, in this case, sorry, forgot to mention that this probability actually depends on the quadratic mass difference given by here. So in a sense, neutrino oscillations only are able to test these values, but they are not able to look at what is the actual scale, what is the actual values of the masses of the neutrinos. But OK, so our task, if we want to create some experiment, we would like to measure this mixing angle that is related, let's say, to the spring constant, and the frequency that is related to the length of the pendulum. So what we can do is basically create some sort of flux of new mu's and try to see if we are able to see this oscillation. And when we see, let's say, this dip, we'll be able to measure these two parameters in some precision. So how does this work experimentally? So in this experiment, we can create a flux of neutrinos, basically by throwing protons to a target. Because of strong interactions, these protons will create pions and other particles. These pions will decay, producing muons and new mu's. And we put some shielding in order to make to avoid the presence of these charged particles. And after that, we put a first detector to control what is the initial flux of new mu's. And if we want to test this hypothesis, if neutrinos are really changing flavor, where they are basically traveling some distance, we can put a second detector and see if we are able to see there the presence of new other flavors besides the flavor that were created initially in our flux. So if we compare the flux of new mu's in the second detector to the first detector, we can basically extract what is called disappearance or survival probability. And if we want to see the other flavor, we will see sort of an appearance probability. So this is basically the technique that is used in several experiments. I will just mention a couple of experiments that will come back later. So the first experiment is the experiment NOVA in the United States. Basically, they are throwing a flux of neutrinos from Fermilab to Minnesota. And it's basically the same idea. So the idea is always putting a near detector, a far detector. In this way, you can control some systematic uncertainties. A second type of detector is T2K, which is an experiment in Japan. And basically, they are producing a flux of neutrinos in one side of the island and throwing to the other side of the island to the super Kamikaze detector that I was talking before. So how an experiment will look for these oscillations? So basically, when you look at this green spectrum correspond to expected events without oscillations. And when you include the oscillations, you see that there is the same dip that I was talking, that it was coming from the probability that I was putting. So here, again, if we are able to compare the number of events here with the dip, you can extract this value of the mixing angle. And where if you look where is the dip located in the reconstructed neutrino energy, you can extract what is this quadratic mass difference for this specific case of neutrinos. OK, so basically what we have seen here is that first, neutrinos were assumed to be massless. But experiments, first with looking for atmospheric neutrinos, noticed the existence of this anomaly. And now we can prove if this anomaly is really what we are thinking, if this means that neutrinos are actually massive particles. And we are able to test it using a more controlled environment, which is basically this accelerator neutrino. So this is basically the idea of the journey that has been so far. There are, of course, other types of neutrino experiments that not only consider these accelerator neutrinos, some consider solar neutrinos or reactor neutrinos, or reactor antineutrinos. And basically, we can have a clear picture of these mixing and masses of neutrinos that I was talking at the beginning. So what is the status of this neutrino mixing, let's say, this year? Basically, we know that there are basically two mass splittings, different from zero. Let's say this is what is called the solar mass splitting and the atmospheric mass splitting, because basically they appear in two different regions, two different scales. And we know that there are basically three mixing angles, because at the end we have three flavors. So it's like having a 3D rotation. And as you can see here, I'm just showing what are the darker region correspond to the 1 sigma extraction after doing some global fit, and the 3 sigma structure is the lighter color. But as you can see here, there's one mixing angle that is very well measured, and actually has the same relative uncertainty as in the quark sector. There are mixing angles that are still a bit far from being clarified what is their value. Also, and perhaps more importantly, since this mixing can have CP violation, you can extract what is the value of this delta CP violation looking at the data. But still, the picture is not clear, although it's pointing out with some specific cases to maximal CP violation. However, as you can see here, there are usually two panels corresponding what I'm calling normal ordering and inverted ordering. And the reason is that we still don't know what is the lightest neutrino. By this, I mean we can have two arrangements of these neutrino masses, basically the mass of nu1, nu2, and nu3. And we don't know if the lightest neutrino is what we are basically calling this nu3, which is least composed by electrons. Sorry, I forgot to put the colors also. Blue is nu-e, yellow is nu-mu, and red is nu-tau. So the heaviest can be the one that is the least composed by this nu-e, or can be the lightest. So what is this called normal? Basically, because it follows the same pattern as the other charged lepton. So the lightest is the electron, then mu, and then tau. And this basically will be the lightest that is, let's say, more associated to electrons, muons, or taus. And this is, of course, now inverted because the lightest would be the most associated to taus. So in this case, we don't know still what is this ordering. Future experiments are planned, and some experiments are actually running now to try to differentiate between these two orderings.
So can I ask a question? So
yeah.
I remember hearing more or less about this 10 years ago, or maybe even longer. What has been learned over the last 10 years about this?
There are some hints, but I mean, statistically it's not significant. But right now is that there is a bit of a preference from the normal ordering, but still our data is not enough to rule out the inverted ordering. Okay. Yeah, so I didn't put like chi-squares, but yeah, there is a bit of a preference for the normal. But now there is an experiment running, well, it will start soon, that is called Juno, that is hope to basically solve this, and then you have the future like Dune.
And does it just take so long to build an experiment? That's why there hasn't been any progress?
Yes.
I see. Okay,
yes. It takes some time, and neutrinos are weakly interacting, so in order to gather all the statistics, it takes some time. Yeah, so now coming back to basically accelerator neutrinos, I just wanted to show that these are the recent T2K data. And as you can see here, well, These are the data, and they are following the pattern that I was showing before. So the blue histogram here is the case without oscillation, and the red is basically the same pattern that I was showing you before, which has the dip. But still, the events are not many, and because of neutrino oscillations, are reduced. So still, this experiment is running and trying to look for this and trying to understand, to extract some parameters from this data. But something that related to the question before is like, how do we, can we extract this ordering, and if it's related to the value of the CP violation? So a work that we did, I don't know, a couple of years ago, that is still the state of the art, it showed that when you look at the data from T2K and the experiment NOVA independently, they basically preferred each one normal ordering. But statistically, when you combine them, there is a preference for the inverted ordering with maximal CP violation. So it's not like very significant, as you can see here, from the values of delta chi-square. But the idea is that still the data is not, we have not enough data to clarify the situation. This is basically the main message here. We still need more data from these two experiments and build other experiments that we could tell us about how you can have, what is the actual ordering and what is the value of delta CP. Because as you can see, there are big correlations between this and also this mixing angle, theta 2, 3. Okay, but so far I have been a bit, let's say, experimental, because I'm talking about experiments, results from the experiments. But let me just go back for a bit about the first question that I was asking, about what is the origin of neutrino masses, right? So as I was saying, I think that the neutrino masses might be not related to the same mechanism that gives masses to the other charged leptons. But in principle, we can see why. So let's say, what is the origin of neutrino masses? So I will just try to draw different ways to produce neutrino masses. The first way is, let's say that basically you just add right-handed neutrinos. You do the same Higgs mechanism as you do for the other charged leptons, and then what? What is the problem? So let's say that, as I was showing before, there's this huge gap between the charged leptons and the neutrinos. And this gap basically, if you want to explain this gap using the same Higgs mechanism, you would need to explain why you have Yukawas that are very, very tiny, 10 to the minus 12. Also, you need to explain why the lepton number is conserved, because you are only introducing right-handed neutrinos, and you are not adding anything else. You need to explain why lepton number is conserved, because we know that this is an accidental symmetry, and actually, if it's a global symmetry, will be broken by gravity. So maybe there is another option in which you can have a sort of the same origin. Let's say you just basically copy the Higgs doublet to a second Higgs doublet, and you assume that instead of having a scale, the electroweak scale, you have a new scale that lives at the electron volt scale. So you can basically put this second Higgs doublet with this new BEV, this new vacuum expectation value. But the thing is that you find that it's not that easy, because at the end, when you have a second Higgs doublet, there is mixing between this second Higgs doublet and the standard model Higgs, and this can lead to problems with electroweak precision data, as we prove in these papers, with all papers now. So maybe this is a complicated situation. Maybe we need to think in a different way. So maybe neutrino masses come from a high scale, and how can this high scale be manifest in, let's say, now our standard model Lagrangian, adding, which is extended to add neutrino masses? So maybe there are some effective operators, and the first effective operator is the dimension 5 operator, the Weinberg operator, which basically will tell you that neutrinos are Majorana particles, and I will come back in a bit what this means. And this tells you that if there are, for instance, these right-handed neutrinos, these new degrees of freedom, and you add a mass term for this, because it's basically not forbidden from the standard model gauge symmetries, if you have a scale of, let's say, the GAT scale close to the GAT scale, 10 to the 12 GeV, what you see is that in principle you don't need to have these Yukawas that are extremely tiny. And this would be a way to test, to explain why the neutrino masses are so small compared to the electroweak scale. There are interesting consequences from this high-scale scenario, because in principle, the existence of this right-handed neutrino, and if it's close to the gut scale, it could explain the observed matter and antimatter asymmetry via what's called the leptogenesis mechanism. Let's say a fourth situation in which we can consider is, let's forget that there exists a high-scale physics. Or maybe, of course, there should be a high-scale physics, but maybe this high-scale physics is not related to the neutrino mass. Maybe what happens is that there is actually a low-scale physics that is talking to neutrinos, but you only have this, let's say you have these new dark sectors that basically are giving the neutrino mass, and these dark sectors only communicate to the standard model sector via what is called a neutrino port. So how you can test this? Principle, you can look for the modifications in your oscillations that I was talking before, these neutrino oscillations, and also in neutrino scatterings. So let me just, let's say that these are some ways that you can give neutrino masses, but in my opinion, there is a more fundamental question that we need to ask, and actually, if we are able to solve this fundamental question, we would be getting some aid to clarify this situation. What is this fundamental question? Well, we don't know if neutrinos are Dirac or Majorana particles. So since now we know that neutrinos are massive particles, and they are the only neutral fermions that we know that exist so far, fundamental fermions that exist in nature, the fermionic nature can be two ways. The first way is like was proposed by Dirac, in which basically you have that particles and antiparticles are different, or let's say in a bit more technical way, if you start with a left-handed neutrino, and you apply the CP transformation, you get a right-handed antineutrino. Or if you do a Lorentz transformation, you get a right-handed neutrino. So the question is, if these two degrees of freedom are the same or not. If they are different, when you apply these two types of transformation, this fermion is actually a Dirac fermion. A second possibility, which was introduced by Majorana, is basically tells us, since these particles are neutral, you can have that the particle is the same as the antiparticle, or if you look back to this, is when you apply these two transformations, we have that the state that you obtain after doing a CP transformation or a Lorentz transformation are the same. So you only have half the degrees of freedom that have in the Dirac case. One point that is very important here is that in the case of Dirac, you can associate the existence of lepton number. And in this case, if neutrinos are Dirac, the lepton number will be conserved. So just remind you briefly about lepton numbers. In any, what we have seen so far in any weak interaction, there is the conservation of this number, which basically tells you that particles are created with, let's say, plus, and antiparticles with minus. And all, when you look at the whole decay, for instance, of pions, there is no if there is no initial lepton number, there will be no final lepton number. However, for the case of Majorana, since you have that particles and antiparticles are different, lepton number will be violated. So why don't we know this? The reason that we don't know this is that weak interactions are chiral, as I was talking before. There is parity violation. And we know that the energy scales in which neutrinos are produced are higher, much higher than their masses. So in principle, let's say in a weak interaction, for instance, the beta decay that I was talking before, you will produce mostly a left-handed neutrino plus a tiny amount of this right-handed neutrino. If you were able to measure this second, you would be able to test this. However, as you can see here, this is basically suppressed because the mass of neutrinos is very small and the energy they have is very large. So the production of the second right-handed neutrino is basically very, very negligible, basically. So in principle, you would be able to see this. Or in other ways, neutrinos behave as non-relativistic, as ultra-relativistic particles. So they behave mostly as massless particles in weak interactions. So how can we solve this? Well, maybe instead of looking to the usual neutrinos, we can look for non-relativistic neutrinos. Try to see if we're looking for these non-relativistic neutrinos, since the effect of Majorana and Dirac will be very significant there, you can look to see if you are able to measure these non-relativistic neutrinos. As far as we know in nature, in principle, There is one type of relativistic neutrinos that is basically the cosmic neutrino background that it was produced in the early universe. And there have been proposals to detect this cosmic neutrino background using this inverse, neutrino capture, in which basically you have a neutron that captures a neutrino and produces a proton and this electron that can be observable. And people have noticed that since these neutrinos are non-relativistic, the difference between Majorana and Dirac will be a factor of 2. When you compute the capture rate for Majorana neutrinos, you obtain that it's twice the capture rate of a Dirac neutron. The reason is that when you look at the history of the universe, you see that what happens is for the Majorana case, since there is no difference between particles and antiparticles, you are able to capture all the cosmic neutrino background that there is. But if neutrinos and antineutrinos are different, you are only able to capture half the cosmic neutrino background because the other half is basically our antineutrinos, and this cannot be captured via this reaction here. However, we noticed that if you allow for the existence of some BSM physics, some interactions that are very let's say, unconstrained, it can happen that even if neutrinos are Dirac, you can have these new interactions can increase the capture rate of Dirac neutrinos and get it close to a value of Majorana. So in principle, it wouldn't be like a 100% test if neutrinos are Dirac or Majorana. So are there other ways to test if neutrinos are Dirac or Majorana? I will come back to this by the end. So now I've been trying to establish more or less what is the current status of neutrino physics. So now we can wonder what lies in the future. So in my opinion, the most important task is try to decipher the source of neutrino masses. So why neutrinos have the masses that we are seeing, and why we have this new scale, the electron volt scale, that's basically related to the neutrino mass. There are several possibilities in which you can look for this. The first is if you, for instance, assume the existence of this light scale physics, you can, as I was talking, you can have effects in oscillations and scattering experiments in the future.
Sorry, I have a very nice question.
Yeah.
Can you go back to the previous slide? So that factor of 2 there,
Mm-hmm.
is that a hidden assumption that if neutrinos are Dirac, more or less half are nus and half are nubars?
Yes. The thing is that when you look at the production of the cosmic neutron background, you assume that the amount of neutrinos and antineutrinos that were produced is the same, right?
And that's
yeah, but
it's obvious. It's not so obvious to me.
Well, it's basically weak interactions. If the universe was an MEV scale, basically you have the production of neutrinos and antineutrinos in the same way. It's basically weak interaction because your fundamental soup would produce neutrinos with all the flavors and antineutrinos, right?
It's probably a very basic question, but we don't see as many positrons as electrons, right? So
yeah, but the primordial plasma, well, you assume that you had a similar amounts. Not this. Yes, they are in thermal equilibrium. Yeah.
Do you have to assume anything about the chemical potential?
In principle, you don't. For this, people don't assume the existence of chemical potential because, yeah, chemical potential would bias the production of neutrinos over antineutrinos. But in principle, the chemical potential would change. Well, yeah, I'm not sure if it would change significantly this, but yeah. Yeah, so in principle, since there is thermal equilibrium, you have the same amount of positrons and electrons in this bath. And then, of course, you can have the scattering of different scatterings that produce neutrinos. They produce neutrinos and antineutrinos in the same way. So in principle, you assume that this is an assumption done in those papers, that the amount of neutrinos and antineutrinos that were created as relics is the same, right? So if neutrinos are Majorana, basically you don't have neutrinos and antineutrinos. You are just calling the two things with two names. So that's why you have one value. And in the Dirac case, you have neutrinos and antineutrinos which are different. And this type of capture can only capture neutrinos. So you only capture like half of the cosmic neutrino background you assume there is. Yes, 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 yes. yes, yes. Okay, okay. Okay, so one possibility, as I was mentioning before, is like we can look in more detail neutrino oscillations and scatterings. And to use this, I think we need to look at the new technology that is being put forward in new experiments that will detect neutrinos. One specific case that I will have working on in several works is like considering the deep underground neutrino experiment, or DUNE. Basically, this experiment, it has the same structure as I was talking before. You have a near detector, and then you throw this new flux of neutrinos first to a near detector and then to a far detector now in South Dakota, and you look for the difference between the fluxes of neutrinos here and neutrinos here in your far detector. The crucial thing of DUNE is that they will use a new technology, but not, let's say, not very new, but it's a technology that is now in development, which is the liquid argon technology. And this new technology is quite interesting because it allows, when you have then a neutrino and interacts with, let's say, the argon nucleus, it produces particles, and these particles can be identified. You can have a 3D reconstruction of these neutrino interactions. Besides, you will have an excellent particle identification. You will be able to separate between muons, electrons, photons, protons. Even people are talking even about neutrons. And you have low energy thresholds to look for some particles like protons. So you can have even the measurement of very low energetic protons like, I don't know, 30 MeV of kinetic energy. However, there are some caveats because since basically these experiments will be huge tanks of liquid argon, you will need to know very in detail the nuclear physics because neutrinos will scatter off the whole argon nucleus, not, let's say, a proton, what happens in super K. And then many, let's say, complicated nuclear physics enters into the game and makes these things complicated. So, yeah, so I think you have, but this, yeah, this is an event. You have basically a production of a neutrino hits here. You have, I think these are pions. Then you have a proton, a low energy proton. So the more reddish is the more energy deposition you had. And these people can look, this is the way that you can have identification because when a proton basically gives the energy to the liquid argon, it gives it in a specific way. And then the size of the track, you see that this size that can tell you what is the energy of the proton. And this is basically an electron. Basically, the electron lives here and starts to shower. So in this case, we know that this will be a new E that interacted because it's producing an electron. So as you can see here, it's a bit complicated, right? Because the interaction of one neutrino is producing a bunch of particles, and you have to reconstruct all this. But on the other hand, it's very interesting because looking at this, you are able to know what is the incoming neutrino direction, right? It's clear where is the neutrino coming from. Yes, because you won't see an electron. You will see a muon, which has a different shape than this. So for instance, muons basically don't shower much. And if they are low energetic, basically you see the decay. So you have the muon. In that case, you have like the muon. And at some point, you see a kink, which is the electron produced from the decay for the muon. So you have so in principle, you can look for these specific things in this technology, in this liquid argon technology.
And the photons are important because there's
Yeah.
the whole thing about.
Yeah, so the difference with a photon is that, in principle, you see that here the electron is always, you have a continuous line. And this is because the electrons are ionizing the liquid argon. If you have photons, you see a gap. So there would be a gap between the initial point of the interaction at some point, because the photons basically don't ionize the liquid argon, but at some point start to shower as well. So you see, like, in that case, you have, I don't know, particles, right? And then you see some gap, a bit of a track, and then the shower. So in this way, you are able to identify, because of this gap, you are able to identify a photon.
But the photon detectors that are, hookahs are important for you?
Yeah, because they will help also in detecting this as well, right? If you have lower energy, yes. So actually, let's say, a smaller version of this is being tested now because there is the SBN program, which is basically is composed by 4 experiments. And the near detector is called SBND, short baseline neutrino detector. It's also using this Arapuca technology. Yeah. So as I was saying, the main caveat of this, and let's say that the main purpose of Dune is try to measure the delta CP phase independently of everything and try to have a 5 sigma signal. But there are caveats, and the main caveat is the nuclear physics, because we really need to know what is the interaction of a neutrino with the whole argon nucleus. But again, it's like we have a good thing and a bad thing. We have this sort of bad thing that is this problem with the nuclear physics, but we have this new technology that is allow us to reconstruct in this very well manner the neutrino interaction. So maybe we should look for other neutrinos that, let's say, you in principle have more control, and you should, in a way, we need to be creative and try to maximize this liquid argon technology, even though there are these caveats for any neutrino that we see. But maybe if Dune measures delta CP, how are we sure? Maybe with the same experiment, we should look for a different kind of neutrinos that from which you can also extract delta CP and compare your results between these beam neutrinos, which is basically these accelerator neutrinos, and other type of neutrinos. So one thing is that maybe we shouldn't forget yet about atmospheric neutrinos. So maybe one can ask, I was talking about Super K and how they basically told us that there's existence of this anomaly that led us to the discovery of neutrino oscillations. So maybe one may wonder, is there anything left to understand about these neutrinos? And the answer is actually yes. The thing is that Cherenkov detectors, in order to see a proton, for instance, the proton that will produce a Cherenkov radiation needs to have a large energy. But if you look for neutrinos that are very, let's say, below the GeV scale, so sub-GeV neutrinos, they won't shower, the production of these protons won't create any Cherenkov radiation, and so it will be difficult to point out where the neutrino is coming from. So this is why experiments like Super Ks are not precise in measuring these sub-GeV neutrinos. However, the physics of these neutrino oscillations for these sub-GeV neutrinos is very rich. Because when, for instance, you compare the oscillation probabilities for the beam and you compare the oscillation probabilities for atmospheric neutrinos, you observe that the delta CP has a small effect here. So the black line corresponds to the oscillation probability without CP violation, and the red corresponds to the case with maximal CP violation. But let me just try to show you what are the probabilities here. The probabilities are very small. So in order to look this difference, you need a lot of events, and this is one of the reasons why we haven't measured delta CP yet with high accuracy. But when you look at the effect of delta CP in these sub-GeV atmospheric neutrinos, let's say that the effect of this is different. It manifests in the difference between oscillation probability, for instance, P mu e, which is basically the oscillation between a nu mu going to a nu e, compared with an oscillation probability between a nu e going to a nu mu. If there is no CP violation, these two probabilities are basically the same. And if you have a CP violation that is different, these two probabilities separate. The reason for this is that matter effects basically violate CP, because we know that matter is made of matter, not antimatter. So when you apply a CP transformation, you don't see the effect. So here, matter effects are what are driving this difference between these two probabilities.
So I have two questions, actually. So what is the energy spectrum for the neutrinos produced by Dune?
So the peak, in principle, is about 2 GeV.
It's 2 GeV.
Yes.
So, but you have sub-GeVs also?
Yeah, there is a bit of sub-GeV. Yes, it's a broad spectrum. Maybe, sorry, I actually maybe I have it here. Sorry, I'm going to spoil my talk.
Sorry about that.
No worries. So here, this is the beam of neutrinos from Dune. And then you see that it's very broad,
It's very broad.
between 2 and 4 GeV.
Okay. And then the other question is about delta CP. So if you put back your slide that you're measuring delta CP in the oscillation of neutrino electron to neutrino muon, etc. But is there a possibility of actually, I don't know about this, if Dune can actually produce the opposite antineutrinos instead of neutrinos and measure directly, not because of this oscillation effect?
But that's what they basically do, right? So although this probability it's important here, you can instead, what I was showing before, you tune, let's say, your shielding to only let pion pluses to be produced and no pion minus.
Right.
Then you can change, basically you change the polarization, and then you have a flux that is mostly done of neutrinos, and the other one is mostly done of antineutrinos.
Okay.
The thing is that there is a bit of contamination of the other antineutrinos. So actually, let me go back to here. So here is basically, sorry, it's a bit confusing, but the blue line, that full blue line, corresponds to nu mu's in a nu mu beam, and this red corresponds to anti-nu mu's in a neutrino beam. So as you can see here, even though it's sort of 2 orders of magnitude, there is still some contamination of higher end.
Yes.
So
yes, because of, I was thinking about that too, because muons can decay in between, right? And then can produce. Okay.
Yeah, you always have this contamination. Okay. And it's even a bit worse when you go to the anti-neutrino mode.
Okay. So, but Dune is planning to do this, inverting the neutrino to antineutrino, and then measure delta CP without relying on this.
Well, it also relies at the end because, sorry. So the probability, what you want to see is basically if the antineutrino probability of this. And the order, sorry, I forgot to put the figure. Right. But the order is the same. The oscillation probability of anti-nu mu to anti-nu e is also about the same order.
Okay.
So it's still even difficult. So the effect is always a few percent. Yes.
Okay. Thank you.
And now how can I go? Do you know how can I Control L? Yes. Nope. Okay. Yeah. It was easier. Okay. Sorry, there was an animation here. I just wanted to show what happens if you change the path of neutrinos. And the idea is that you always, sorry, let me just move this. Yeah. So you see that not only the effect of the delta CP separating this effect of delta CP also depends on where these neutrinos are coming from. So this is interesting because if you are able to tell where the neutrinos are coming from with some let's say, some accuracy, you would be able to separate what is the factor or the effect of delta CP in these two probabilities. Okay, so the idea is that here maybe I can show this with this spectrum. Basically, this are like our predicted number of events in this paper with between 2 values of delta CP. And these are basically the statistical error bar. So as you can see here, if you have different beams, I don't remember the numbers. I think this is like crossing only the mantle and core of the interior of the Earth. You see that the effect is different. So if you have 2 values of delta CP, and if you are able to look at each, let's say, if you are able to see the dependence on this zenith angle, you would be able to extract what is the value of delta CP. And this is more or less what we got here. Although we were putting like a true value, this maximal CP violation, you see that there are regions that even with this setup of Dune, you are able to exclude at more than 3.
So this is for the 4 modules or for 2 modules?
Yeah, this is 4 modules and 10 years.
4 modules and 10 years.
Yeah, it's not really, yeah, it's 400 kiloton year.
Thank you.
Yeah. So yes. So our sensitivity, the thing is that it's also coming from what I was talking about, the separation between electrons and muons, the 2 probabilities, right? And in a certain way, it's also coming from the separation between neutrinos and antineutrinos. But it's not a direct separation because in principle, you cannot turn off like the atmosphere and fix what is your flux of neutrinos and antineutrinos. But because of the properties of liquid argon, you can have events in which you see protons, and this will be related to neutrinos, and you see events where you only see a lepton, like electron or a muon that is produced in the reaction, but you don't see any proton. So in a statistical way, this is telling you what are coming from neutrinos and which are coming from antineutrinos. And because of this, let's say, synergy between these two topologies, we are able to separate neutrinos from antineutrinos and get some sensitivity to delta CP. And again, this is like a free. We don't need to have any beam. It's basically having the 4 modules there, and you can look for this, because at the end, is neutrinos, atmospheric neutrinos are there. And the thing is that as we pointed out, there is still things to learn with these atmospheric neutrinos. OK, so let me just move from the far detector now to the near detector and understand what kind of physics we could do there. One of the nice things, if we, again, look at the beam neutrinos, is that the amount of neutrinos that we expect is huge. So the events that you will have in this near detector are also huge. And then we can even look for doing a precision measurement with neutrinos. And we can do this using neutrino electron scattering, which is basically this type of interaction. Or you can look for these rare events as the trident interaction. Basically, you have an incoming neutrino, and it produces a pair of charged leptons that you can look for in your detector. So,
say a little, what did you do in these papers? I mean, are they just Feynman diagram computations?
No, of course not.
So what is in the papers?
So what we did is, using this technology, because the near detector, we have some specific features, like you are able to move your near detector, you will be able to measure, to change what is the flux of the neutrino that you have. Like in this shape, you have a flux, let's say, more broad, and then when you start to go off axis, you have a different type of flux. You are able to separate statistically the amount of electron neutrinos and muon neutrinos. And because of this, you are able to measure what is the, for instance, you are able to measure what is the mixing angle, the weak mixing angle, and low momentum transfer. So this is a new way to, well, let's say it was noticed before that you can do it with the neutrino electron scattering. But using this specific way that the near detector is set up, you are able to extract with some accuracy that is, it's even comparable with other experiments that don't use neutrinos. So this is what we did in this first paper here. So it's more, of course, not computing cross-section because it's not complicated, but it's using the ideas of having this setup for the near detector and exploiting them in a different way, let's say, in a smart way. And also, since we would be able to measure this new type of scattering, yes. Yeah, well, it also helps in the sense that with this, if you are able to reduce some systematic uncertainties. Because you can have, for instance, you can have a better measurement here because the flux is very peaked at some energy that you know. So in principle, you are able to better measure neutrino argon cross-sections. So this is the main purpose of moving this detector, like trying to reduce systematic uncertainties, right? But we were proposing another way to use it, exploiting to actually extract physics. Another case that I was talking is like the neutrino, the trident interaction. And it's interesting to point out that only this channel in which you produce a pair of muons have been seen so far. The other channels, when you have, I don't know, a pair of electrons or one electron and one muon, have not seen yet. And we have shown that first, you would be able to see a large amount of events in the near detector of these channels that haven't been seen yet. So because of since this cross-section are growing with energy, and as I was talking before, the dune beam is very wide, in principle, you would be able to see this. But perhaps more interestingly, if these scatterings, since they are very rare, and if there is some beyond the standard model physics that modifies them, you are able to test, for instance, the existence of L mu minus L tau boson, right? With this, using this rare scattering. And this is something that collaboration has taken into account now. Yeah, it's included in the main program of the. Okay, a second possibility, is besides looking at oscillations and scatterings, is looking for neutrino astrophysics. So maybe I need to rush a bit. So as I was talking before, one of the more interesting questions that we have is like, we need to solve is understanding if neutrinos are Dirac or Majorana particles. However, there is sort of an intermediate scenario in which neutrinos are Majorana but behave mostly as Dirac, which is called pseudo-Dirac neutrinos. So what is this? Basically, you can see a Dirac fermion as equivalent to two Majorana fermions, which are basically degenerating mass. Basically, you have a Dirac, let's say, neutrino is composed by two Majorana neutrinos, which have the same mass, but the opposite CP parities. But if there exists some BSM physics, it can basically break this degeneracy between the masses, and if the breaking of this degeneracy is small, this can lead to some observable consequences. This is what is called pseudo-Dirac neutrinos, and there are some limits on the splitting that you can have when you look at different experiments with solar, atmospheric, of high energy neutrinos. So our idea is that basically, as I was mentioning, instead of having a new one state, it's like when you look at the hyperfine structure, right? Something is basically splitting this one new one into two, and then you have this tiny split. So what would be the consequence of having this new tiny splitting? Of course, if you have a new tiny splitting, you can also have the existence of neutrino oscillations, right? But maybe these neutrino oscillations don't span distances that are achievable at the Earth, but basically they only appear when you have distances that are astrophysical or cosmological distances. So here I'm just showing you the distance and the energy of the neutrinos, and these different dotted lines basically correspond to the oscillation length depending on the mass splitting here. So these two red dashed lines correspond to the solar and mass splittings. And for me, I always say when I look at this plot is that nature has been very kind, because these two mass splittings lie within the reach of our experiments. If these mass splittings lie in other place, maybe we would be still thinking that neutrinos are massless. But if we want to look and try to test very tiny mass splittings, we could go for lower energy neutrinos, because of course this is proportional, and then try to look for neutrinos that are coming from very far away. So for instance, neutrinos coming from supernova, and what is called the diffuse supernova neutrino background. So what are neutrinos from supernova? Basically, in the final stages of a star, you can have a star producing an iron core, and at some point this iron core collapses, and because of this collapse, they produce a huge amount of neutrinos. So we know that these neutrinos do exist because we have seen the measurement of these neutrinos from this supernova, 1987A, and about 30 neutrinos were measured with all technology. So if we look at what would be the events of a supernova, let's say, with the future technology, we can expect 10,000 events. And some people say it's like your detector will shine like a Christmas tree when these neutrinos reach. So the question is, when will the next galactic supernova be? This is something we still don't know. So we know that they are rare and about 3% true, but we don't know. So let me just take a look a bit on what is this, the data from this supernova. Basically, we observe about 30 events in a time window which is 12 seconds. And to compare with the normal neutrino experiment, in a normal neutrino experiment, we see one neutrino per day. And this neutrino we saw about 1 per second, sort of about 1 second. So as you can see, the amount of neutrinos that reached there was huge. And many physics has been extracted from these few events. We have constraints on the neutrino mass and lifetime, constraints on how the supernova basically behaves, because if, for instance, there are the production of other particles like, I don't know, light axions or stuff would modify the energy spectrum of these neutrinos. And there are, so those are the limits on beyond the standard model physics. So one may wonder, is there still something to learn? Something that we notice is that people haven't considered the oscillations, this oscillation that I was talking before, that happens if neutrinos are pseudo-Dirac particles. So we did basically in this work the analysis of this supernova data, and we found a very mild preference for an oscillation. It's very mild because when you compare with the non-oscillation case, which is like over here, you have only a delta chi-square of 2 of preference, which is basically nothing. And of course, the reason is that we don't have many events. But even maybe more interesting is that we are able to exclude a tiny range even with these 30 events. The reason is that if you have an oscillation that is compatible with this tiny, tiny mass splitting, you will see huge difference, I think, in the IMB experiments. Like here you see 5 events for some energies, and if you have an oscillation here that will basically oscillate these neutrinos, you wouldn't see any neutrino with these energies. But again, the thing is that we can basically either wait for one supernova or instead look for all the supernovae that have exploded in the universe. And this is basically what is called the diffuse supernova neutrino background. So basically the idea is that we don't expect for one galactic supernova, but we basically look for all the neutrinos, these diffuse flux of neutrinos, from all the supernovae that have exploded since the first stars. And this is something that is basically a new frontier, and we expect to detect these neutrinos in the next decade or so. This is something I am very eager to see if we are able to measure this diffuse supernova. Because at the end, these are the oldest neutrinos that are within experimental reach. Like really, really, we are able to detect, right? The cosmic neutrino background is still, let's say, some dream. It's not very, very easy to detect the cosmic neutrino. But these are the oldest neutrinos that are within experimental reach. So how do you compute these flux? Basically, you depend on 3 branches of physics. You depend on you predict what is the flux of neutrinos from this supernova explosion. It depends on the star formation rate and basically how many explosions of supernova you expect as function of redshift. And finally, of course, these neutrinos are propagating in an expanding universe, so it depends on the cosmology. So when you factor out everything and you do this convolution, you find this spectra for different flavor of neutrinos. Here, nu x corresponds to the other flavors which are not electron. And the bands that we have here is that there is a sort of large uncertainty in this star formation rate. So this is what we have this prediction here. But as I was mentioning, this is a guaranteed flux because we have seen neutrinos from supernova, and we of course see how the stars we see this star formation rate. So this is a flux that we expect to measure, and experiments like Super Kamiokande are looking for this. So what can we learn with this? We could learn first about an expanding universe, because at the end, these neutrinos are propagating in the universe. So in principle, you could look for constraints on cosmology, or even the star formation rate as seen by neutrinos. But of course, when you compare with the constraints that you have from light, you won't be able to win. Then we can look for properties that are related to neutrinos. So in this case, the most interesting things that you can look for are neutrinos properties that are sort of slow, because since these neutrinos have been propagating for a long time. So you can look for neutrino decay, mass-varying neutrinos, neutrino self-interactions, or more to what I was talking before, this scenario in which neutrinos are pseudo-Dirac. So what is the effect of having this additional pseudo-Dirac oscillation here? So what we see is, for instance, for this specific flux, we observe that you will see the same dip that I was talking before that happened in accelerator neutrinos. You will see a similar dip in the flux of new neutrinos that reach the Earth. And experimentally, again, you will be able to see the same dip here in comparison with the events you expect in a future detector, which is hyperchemical. So we have computed what is the sensitivity of these experiments, and we see that they will be able to put very strong constraints on this tiny, tiny mass splitting. So if, let's say that in this way, we are basically reaching the observable universe, because you cannot have neutrinos that are propagating for much longer. So these are like the ultimate mass splittings that you could be able to test, and you can do this with this diffuse supernova neutrino background. But OK, maybe that was a bit fast about neutrino astrophysics, but in order to conclude, let me just go even further to neutrino cosmology. And something that I've been working on that I find quite interesting is like understanding this connection between primordial black holes and particle physics. And it started because I wanted to understand if the effect that neutrinos are Dirac or Majorana would differentiate other processes that are not weak necessarily, right? So for instance, processes that are related with gravity or other processes that we expect in nature. So we started to work on this, and we noticed that, for instance, the evaporation of a black hole will depend if neutrinos are Dirac or Majorana particles. Why? Because black holes don't care about weak interactions. They will produce all particles that are in nature. So in principle, if neutrinos are Majorana, let's say that you have, well, in general, if neutrinos are, you are able to produce neutrinos in two different ways. First, a direct emission from a black hole, or you can have the production of other particles like muons and quarks that basically will create neutrinos after weak interactions. But these are, let's say, not interesting because at the end, the production of neutrinos comes from the same physics we expect with weak interactions. So we can look for this primary component, and we observe if neutrinos are Majorana, you only have the production of these 2 degrees of freedom, right? Because you only have 2 degrees of freedom in the Majorana case. And for instance, if you look at these models with CISO, and if you have, again, heavy right-handed neutrinos, these right-handed neutrinos can be created from black hole evaporation, and this can have effect on leptogenesis. The second possibility is that, again, neutrinos are Dirac particles. So in that case, you will be able to produce 4 degrees of freedom, which 2 of these 4 degrees of freedom are very weakly interacting. Let's say if you assume that you only have these Yukawas of 10 to the minus 12. So they won't even thermalize with the primordial plasma. So we investigated some phenomenological consequences, but I will talk in more detail on Thursday on my Blackboard talk. So to conclude, let me just go back to our journey. At some point, Aeneas got heard about the prophecy of the future of his descendants, in this case, the Romans, and heard that the Romans will create an amazing empire. So we may wonder what is the future of neutrino physics. So I think there are many things to be explored about neutrinos, and I basically summarize in 3 steps, which are related to what I was talking before. Man-made neutrinos. So here, one of the more interesting things is looking for new technology that will allow us to study these particles and try to be smart in exploiting this new technology as the best that we can. Other is looking for neutrinos from astrophysical sources, like the relic neutrinos from a supernovae, or very high energy neutrinos that are and will be a key for multi-messenger astrophysics. And finally, of course, looking for neutrinos in cosmology. As I was saying, the CNUB is what I believe the dream of any neutrino physicist, try to look for these neutrinos and understand how neutrinos, if they are related to the existing matter and antimatter symmetry, and neutrinos and primordial black holes, as I was talking at the end. So what lies the future for neutrino physics? I can't say for sure, but I'm sure it will be brilliant, and hopefully it will bring more Nobel Prizes to the neutrino field. Something just a curiosity is that the other side of the Nobel medal is written this in Latin, which means inventions enhance life, which is beautified through art, which actually comes from the Aeneid, a paraphrasation of this. And that's what I wanted to say. Thank you very much.
Are there any questions online first? So I had a question on that question. So when will there be an experiment which will tell us more information about the data? How long will we have to wait until we have some new facts about neutrinos?
Okay, so as I was mentioning, well, actually, there is this experiment in China called Juno, which is actually now in the commission phase. Basically, they are finishing to building it. So basically, this is a reactor antineutrino experiment, and it's designed to measure basically this mass hierarchy, mass ordering that I was talking. And in principle, this will be by the newest measurement that we expect. So if we have Juno in, I don't know, a few years, let's say 5 or 10 years, between 5 and 10 years, should be able to measure, should tell us what is the mass ordering of neutrinos. There are, let's say,
How much more precision will we have from that than we have in the previous one? Just to understand the order
Okay,
of
so
magnitude.
I don't know if I have.
Is it twice as precise? Or
So the thing is that they will measure things in a different way, because so what I was showing before is like you have the probability, something like this, right? So you have P, but this is an energy, right? This P, let's say mu mu. But this is when you assume 2 flavors, right? Is you only have 2 flavors. But if you have, let's see, I don't have another color. So when you look at the 3 flavor case, what you have is you see there are these tiny oscillations around here. So Juno is expected not only to see this one, but they say that they will have a great energy resolution to measure these wiggles here. So they will be able to measure basically the combination of the 2 frequencies in the experiment. And this is coming from this reactor antivirus.
So can you summarize again, what was the motivation for this quasi-Dirac scenario?
Yeah.
I think I missed it.
Yeah, so the idea is that in principle you can have Dirac fermions, some model with some gauge symmetry that predicts Dirac neutrinos, but you can have higher scale physics, for instance, even gravity, that will basically make a break in between these 2 eigenstates, right? So it will basically, some models basically predict the existence of Dirac neutrinos, but when you include this effective operator, you see that these neutrinos won't be exactly Dirac, but they will have a tiny mass splitting between the 2 Majorana degrees of freedom that exist. So in principle, with this, you would be able to test how much is this breaking, right? So this tiny break. On the other side, this is basically when you look, let's say, maybe I can go to some slide.
So this is not the same as 2 Majorana with similar mass?
Yeah, but they are basically almost degenerate mass, but there is a tiny difference between the 2 degrees of freedom.
But do you have some tuning to make this mass difference small?
Yeah, so maybe when you look at the Dirac plus Majorana Lagrangian, let's say you have your Yukawa terms and your Majorana mass terms, you can build it in the same way, right? But in principle, nothing forbids that the new scale, the right-handed neutrino mass scale, is much smaller than the electroweak scale, right? And actually, this is a technical natural scenario because when this mass scale is equal to 0, you recover the lepton number conservation. So in principle, yeah, you probably require some fine-tuning to have this being small, right? But maybe it's just coming because of the breaking of some effective operator that lives in high scales. Right.
So before, when you were saying that there could be some factor 2 that would distinguish the 2 scenarios, this was before realizing
Yeah,
that
yeah,
this could
yeah. So yeah, actually we are now exploring what happens with the CNUV for this case. Because this is more like the 2 extreme cases, right? Which they're completely Dirac or completely Majorana. So somehow you, in the Dirac case, forbid the existence of these operators that break these degeneracies. They are purely Dirac, or you can have they are purely Majorana. So in principle, it's not a dichotomy, right? Because in principle, there should be a way when you come from one and go to the other. But this is something we're working, like what happens with the CNUV, with the cosmic neutrino background, for this specific case of pseudo-Dirac neutrinos.
And maybe just a more naive question. So what do we expect to learn if we could answer these questions? If you know, it's Majorana, say, and you know some ordering of masses.
Yeah, yeah. So for
then
instance,
what else? What next? Because
no, sorry.
yeah, besides knowing the numbers, why would we care?
Yeah, because Majorana will tell us, for instance, what depending on the scale of the Majorana mass that we find, this will, for instance, what happens is, let me just go back. One more. Yeah. So for instance, some effective operators predict that the neutrinos are Majorana. If we are able to measure that the neutrinos are Majorana, and we are able to measure, let's say, what the scale of the Majorana masses and where is this coming from, we could be able to test if this is related to a GATT scale, right? In this case, for instance, if you observe that the Majorana mass scale is related to a GATT scale, it would be an indication of where is the GATT scale lives. Or if, for instance, you observe something in neutrino oscillation scattering, some deviation, you would be able to start to point out if there is the existence of low-scale physics that is only talking with standard model via neutrinos. And maybe this low-scale physics is related to the neutrino mass because it can also be producing Majorana neutrinos or Dirac neutrinos.
So it's at the same level of learning about the UV completion by looking at the next irrelevant operator in the standard model?
Yes, but basically, yeah, but the thing is that for the neutrinos, we don't know what's the scale. So we can just assume, well, for anything, we don't know what's the scale. But we don't know if it's the same scale that is affecting all the charged leptons and is affecting neutrinos. But because we see this different pattern between the masses of the charged leptons. Charged leptons and neutrinos. So maybe there are two different scales in nature. One is only talking with neutrinos.
Why would that be the case?
Well, I don't know, right? But this is what we are observing now. We're observing that there is the difference between the neutrinos and the charged leptons. So why is that? That's basically the main question we want to ask, right? Because it's not like in quarks. Of course, there is still the flavor problem in the quark sector, but it's not as strong as neutrinos, right? Yeah, there is a difference. We don't know. We don't understand why this pattern. We don't understand why the top is, let's say, the top is more natural from the from the Higgs mechanism. But we don't understand this pattern. But at least we see that they are not like very far apart. But when we look at neutrinos, there are 6 orders of magnitude between the charged leptons and their masses. And these basically are isospin related particles, right? So why is this? It's something I think it's, and of course, if we understand if neutrinos are Dirac or Majorana, this might tell us why this is coming from, if this is okay. If it's because there is this right-handed neutrinos that are living in a higher scale and are suppressing the neutrino masses.
Ricardo, you had a question? Go ahead.
Yeah, very basic question. I'm at home today, but I will meet tomorrow. People often compare the neutrino mixing matrix to the CKM matrix, but I see some stark differences. The CKM matrix connect the up-type quarks to the down-type quarks. There is a change of charge, whereas the neutrino mixing matrix connects the mass eigenstate to the flavor eigenstate of leptons with the same charge. Can you comment on this?
Yeah, because the difference is that how do we know the flavor of an electron, right? We know the flavor of an electron because we know the mass of an electron, right? So what it's basically telling us is that we know that this lepton is an electron or a mu or a tau because of its mass. So this is telling us that the mass eigenstates and the flavor eigenstates for charged leptons, they are basically the same. So you don't have a mixing there, because this is how we are saying if this is an electron, a mu or tau, right? In the case of neutrino, no, we don't have that. So in the quark case, yeah, you have, but then you also have that the quark basis, the flavor basis is different from the mass basis for both up and down type quarks, right? Because we don't know what is the mass or what is the relation between the flavor basis and the mass basis in quarks. But for charged leptons, basically, the mass tells us what is the flavor of this charged lepton. So this is basically when you look at the Yukawas, you have the two contributions, right, from when you do the rotations from the flavor to the mass. But in the case of CKM, you keep it always for both. But for the case of the leptons, you only keep for neutrinos, because you always define your flavor basis and your mass basis for charged lepton to be the same. I hope I answered your question.
Thank you.
I have a naive question. For gut models, what is more natural, having a Dirac or Majorana?
For what, sorry?
For grand unified theories, what's more natural?
Well, it usually depends on the grand unified model, but in principle, you always...
the simplest one.
Yeah. Let's say, I believe you always want to have, well, it depends on actual symmetries, of course, but people, for instance, put this right-handed neutrino in a multiplet, and they find that this will give Majorana masses. So in principle, you always have like Majorana masses producing from this So you always have this Majorana scale because they are singlets.
But the seesaw mechanism is Dirac, right?
No, it's
That's
Majorana.
Majorana,
It's
okay,
Majorana. It's
okay.
Majorana. Yes.
Other question? Okay, so Yuber will give another talk on Thursday at 2:30.
Okay.
Okay, so let's thank Yuber.
Thank you.